This is going to be a quick dive into nuclear physics and particularly nuclear decay. So first we got to talk about what a nucleus is before we can talk about how it decays. So some properties of nuclei is all nuclei are composed of protons and neutrons, except for ordinary hydrogen, which just has a proton. It doesn't necessarily have a neutron. So the atomic number Z equals the number of protons in the nucleus, and this tells us what element it is. The neutron number is the number of neutrons in the nucleus, and the mass number is A. The mass number is basically the sum of the protons plus the neutrons. So nucleon is a generic term for anything that exists in the nucleus, whether it's called a proton or a neutron. And the mass number is not the same as the mass in like kilograms. It gives us an idea of what that is, but it's not the same. How elements are usually symbolized is this way. So often we'll have just a chemical element like aluminum, carbon, oxygen, and that's what this X symbol is. It's the chemical symbol of the element, and that's what you're going to find on the big letters on the periodic table. Then the mass number here is A, and Z is the atomic number. You often won't see the Z written because it's somewhat redundant, because it's going to be the same as the characters. So for instance, here we have aluminum 27. It has 13 protons and a total of 27 nucleotons. So that's how we symbolize it. It's convenient to use a unified mass unit to express mass. So 1U is equal to this many kilograms, based on the definition of mass that comes from one C12 atom, which we could also write like this. It's exactly 12U. The mass can also be expressed in mega electron volts per C squared. So that's just another way to do it. I haven't seen that very much, but we've even used U in this class thus far. So here's a table of the different masses. A proton is a little more than one, a neutron is a little bit more than one, and an electron is teeny tiny. For a nucleus to be stable, it needs to meet certain criteria. So very large repulsive electrostatic forces exist between protons because we have basically two protons and a helium atom that are very close to each other. And so why don't these protons fly apart from each other? We know that there should be a repulsive force between two positive ions. So there is another force holding it together. There's got to be something else that balances it, because if just electrostatics and their Coulomb force was present, they would fly apart. There'd be no way for them to exist together in a nucleus. So that's called the nuclear force. This is an attractive force between all nuclear particles. It's a force between protons and neutrons. And the nuclear force is stronger than the Coulomb force in order for these things to hold together. So nuclei are stable if they meet certain criteria, and basically the more protons you have, the more neutrons you need to dilute out the protons. So light nuclei are most stable if N is equal to Z, so the number of neutrons is equal to the number of protons. However, heavy nuclei are more stable when Z is much bigger than Z. And so you can see that it follows a trend that these are all these dots are the stable nuclei. And it's not until we get down to here where you want equal numbers of both. So as the number of protons increases, so must the number of neutrons, and the number of neutrons must actually exceed the number of protons for stability. As nuclei become unstable, especially those very, very heavy ones, they'll tend to decay, and then they can decay using various types of radiation. If we were to go in this chapter more, we'd go into this in more detail, but we're mainly interested in the half-life discussion. But the first type of radiation is alpha particles. They've been named in order of discovery. So the alpha particles are helium nuclei. This is 4, so it's got 2 protons and 2 neutrons, and it comes off. It's heavy compared to these other radiations, and so it can be fairly easily stopped. And it's stopped by just a piece of paper. The beta particles are either electrons or positrons. It might seem strange that an electron or positron could come out of the nucleus, but that's what we get from energy decay, and we'll talk about that at some other point. So the positron is an antiparticle of an electron. So if it comes into contact with an electron, they'll annihilate each other. It's similar to an electron in every way except its charge is positive. And these things can penetrate a few millimeters of aluminum. So you need to take more precautions if you're working with something with beta particles. Then the gamma rays are the most harmful ones. Those are the ones we tend to be more worried about. And these rays are high energy photons, and they can penetrate several centimeters of lead. And since they're very high energy, they can cause ionizing. They're basically a form of ionizing radiation and can cause DNA damage. So that's the main problem with radiation is the DNA damage that can cause, particularly these gamma rays. Here is a decay series to show you what happens when an element decays with these different types of radiation. So here we have thorium. It goes down to radion. And so here it goes down 4 nucleotides from 32 to 28, and it loses 2 protons in the process, meaning it goes down the periodic table by 2. And then as it loses an electron, basically that forms another proton within the nucleus. And so we go up and we actually go back to thorium. And then we go back down to radium, and then radon, and then eventually to lead, and eventually we'll settle down into lead as the stable isotope that results from this particular decay. And you'll notice that here we have red and radon. And in especially the Dubuque area is known for mining. It was settled originally by Europeans in order to mine lead. And in our particular basement, we have a radon mitigation system. So I guess I'm not surprised that these two things come together if they come from the same series. And this is in a lot of series for radioactive decay.